and welcome back to our journey in engineering mechanics. Today we're going to continue our journey into calculating reaction forces, and we're going to look again at distributed loads. Only this time it's not going to be a uniformly distributed load, it's going to be a triangular distributed load. And we're going to see how that differs from the uniformly distributed load that we solved previously. Let's have a look together. So similar to the previous exercise, I've got a simply supported beam of 6 meters. I've got a roller support at A and a pin support at B. The difference though this time is that I've got a distributed load and it's in the shape of a triangle. Exactly the same method applies here. To get the force, I need to figure out what the area of the shape is, and to find moments anywhere, the distance is going to be the distance from the centroid of the shape. So before we begin, let's just have a look at this force. We can see here that we've got a triangle, so we can easily find the area, and the place that we put the equivalent force or the resultant force of this uniformly distributed load is in the centroid, so here. The centroid of a triangle is always a third of the length from the opposite side and 2/3 from the other side, from the 0 point. And so with that in mind, let's find the reactions. The first thing that I want to do is my free body diagram. So I need to swap out these supports for the reaction forces. So at A I have AY, and at B I have two forces because this is a pin support. So I'll have here BY in the Y direction and BX in the X direction. So let's start finding the reactions. We are in 2D, so we have three equations of equilibrium, sum of forces in X, sum of forces in Y, and sum of moments around a point. The idea here is that we want equilibrium. We don't want our structure to move in the X direction or the Y direction or two perpendicular directions in general terms, and we also don't want our structure rotating. Let's start off with sum of forces in X equals 0, with this being my positive X direction. Here I can see that in X I've got Bx, and I don't have any forces in the X direction in this case, and I don't have any other reactions, so Bx equals 0, and I can highlight that. If I move on to the Y direction, sum of forces in Y equals 0, with this being my positive Y direction, I have AY plus BY in the positive Y direction, and in the negative Y direction, I have this triangular distributed load. Now, as we said, the equivalent force of this distributed load is the area. In this case, I've got a triangle, 10 kilonewton per meter on the opposite side and 6 meters length. So the area of that triangle is 10 kilonewton per meter times 6 meters divided by 2, right? The area of a triangle equals 0. So AY plus BY equals 30. Now I can see here from a unit perspective, right, I've got kilonewton per meter here, I've got meters here, so I can divide by meters and I end up with kilonewtons. So I've got force. AY is a force, BY is a force, and that 30 kilonewtons. Now I can't solve that any further because I need to find a relationship between AY and BY. For that, let's do sum of moments around A equals 0, with this being my positive direction. So starting off with Bx passes through A and it's also 0, so it won't contribute a moment. By contributes a positive moment, and the distance from By to A is 6 meters. So just a reminder, if I have a force in Y, I need a distance in X. The distance is always perpendicular. The sign, the positive, is because if I continue my line of action and try to rotate around AY, I can see that this is my direction and this is positive in my sign convention. So plus By times 6. With that same method, I can see that the distributed load contributes a negative moment, so minus. I need to calculate the area because the area gives me the force. So minus 10 times 6 divided by 2, that is the force. And then I need to times by the distance. Now, as we said when we looked at the centroid, the distance is the distance from the centroid to where we're looking. So in our case here, the centroid of this triangle is, say, somewhere here, and this is the distance, right? It's the perpendicular distance to the line of action of the forces. In our case, it's a third of 6. So times 1/3 times 6. So this is the distance, and in purple we have the force. And that needs to equal 0 because this needs to be in equilibrium. So here we get that 6 By equals 10 times 6 divided by 6. So I see here that these two 6's go, and I can also divide this 6 with this 6, and I end up, as you can see, with By equals 10 kilonewtons. Once I have that, I can go back to my previous equation and say that Ay equals 30 minus By, and that is 30 minus 10, so Ay equals 20 kilonewtons. A little sense check here. Ay is bigger than By, so if I look how this distributed load is laid out, I can see that the bulk of the load is next to A, so it makes sense that closer to A, the reaction force would be bigger. I can also look at the units and see that everything worked out as kilonewtons, which is exactly what I'm expecting in these force reactions. The last thing I want to do before we finish off is a check. And I'm going to check this by doing the sum of moments around B. And that should equal 0 as well, right? Because we're in equilibrium. So if I look at the moments around B, I've got minus Ay times 6. And then I've got this distributed load. So first thing, the area, 10 times 6 divided by 2. That gives me the force, which equals the area, and then I have the distance. Now, this time the centroid is still here, so it's going to be 2/3 of the length. So times 2/3 times 6, and that is the distance. And all of that obviously needs to equal 0. So in this case, we've got 6Ay equals 10 times 6 times 2 times 6 over 6. And I can see here that this 6 and this 6 go, and I can divide by 6. So I've got this 6 and this 6. And so we can see here that I am left with Ay equals 20 kilonewtons, which is exactly what I got before. So that means that my calculations were correct, and I've also checked them. So now the last thing I need to do is replace these reaction forces with their values. So Bx worked out as 0, so I can just get rid of that completely. Ay was 20, so that's 20 kilonewtons here. And By was 10, so 10 kilonewtons here. And that's it. We've solved this simply supported beam with a triangular distributed load. So hopefully that's helped clarify that as long as you know the shape of your distributed load, you can calculate the area, which gives you the equivalent force of that distributed load, and the distance is always going to be the distance from the centroid of that load to wherever you're looking for moments. So as long as we maintain that knowledge, we can find reaction forces wherever we have 3 unknown reactions, 3 equations of equilibrium, and any distributed load that we know to calculate the area and find the centroid for. So hopefully that's been helpful, and hopefully you'll join me again to find more reactions and solve some more structural engineering. Bye for now.